Go Lakers! I just want to remember that this is the video the day after the Lakers won the 2020 NBA championship. All right, student people, get your periodic table ready because today we're going to be studying periodic table trends. All right, students, let's go ahead and think about what the word trends means for a moment. We're studying periodic table trends. Another word for trends you can say is patterns. And there's definitely some patterns that you may have noticed in the periodic table so far. For example, we've been studying the atomic number and the number of protons. So if you go from left to right and then down each row, you can see that the number is increasing in order. And it's not increasing in order just to keep them in numerical order. It's increasing in order of mass. So the lightest elements start at the very top, and you get heavier as you move on. Why? Because the number of protons is increasing inside of the nucleus of each of the elements, which means that the mass is increasing. So one of the trends or patterns that we've already studied in the periodic table is that the periodic table increases by mass because the number of protons and the number of neutrons and electrons are also increasing as you move from box to box on the periodic table. All right, but the first trend we're going to be talking about today is atomic size. Atomic size, and that's just actually referring to the size of the atom. So we'll take like lithium atom, for example, and we'll draw the shells and the electrons. Okay, just put it off to the side right there for fun. So we're actually literally talking about the size of the atom. Whoop, not that one. There we go. Like how big it is. Measuring the size. Okay, and the size depends on two things. The number of shells. So, for example, lithium being on the second row, we know it has 2 shells. Well, lithium is going to be larger than any of the elements on the first row, but it will be smaller than any of the elements on the third, fourth, fifth, sixth, or seventh row. Here's an example. Lithium right here. Hydrogen is smaller since it's on the first row. Helium is also smaller, but sodium is larger. Potassium is larger. Strontium is larger. All the ones on higher rows are larger. All right, another thing that atomic size depends on is the number of protons within the row. Okay, and something to keep in mind when we're talking about this is that protons mass is 1. We'll say 1 atomic mass unit. Okay, while electrons mass is negligible, meaning that it's so small and so non-massive that it doesn't even compare at all to a proton. So protons are way more massive. Okay, why does this matter? Because we know that positive charges attract with negative charges. So if we imagine our an element with the, I'll draw over here, with the proton in the middle and the electrons on the outside, they're attracting each other. So this is an attractive force because the electrons are negative, protons are positive. So it's those protons in the nucleus that are keeping the electrons from, like, say, flying away and going somewhere far away. Okay? So the more protons that are in the nucleus means that that element will have a stronger pull on the electrons that are in the electron cloud. So we'll give an example like this. So lithium, with its, let's just actually, instead of drawing lithium, we'll just draw 3 protons for lithium in the center. And then it has the first shell and second shell. So lithium's protons are keeping those electrons pulled in tight. But if we moved over to, say, nitrogen, for example, with 7 protons, nitrogen also has 2 shells. Okay, so there's the nitrogen atom. Nitrogen's 7 protons in the nucleus have a stronger magnetic hold on the electrons in the electron cloud. So the nitrogen atom is actually going to have a smaller atomic size than the lithium atom. Okay, so that's the reason, right? So this is larger. Okay, and we were comparing 2 atoms within the same row. So that's why we said something that the atomic size depends on is the number of protons within the row. So if we're looking at lithium here and nitrogen over here, we know that lithium is larger because it has less protons, meaning that the electrons in the electron cloud could kind of escape that electromagnetic pull of the protons farther than the nitrogen's electrons could. So, looking at the periodic table, the trend or the pattern that we see on the periodic table is that atomic size increases as you move down the rows because more shells um, are present. But within the row, the atomic size will decrease as you move from left to right. So the atomic size will decrease as you move from left to right, but it will increase as you move down in increasing shells. All right, the second periodic table trend that we're studying today is is electronegativity. Electronegativity. Okay, electronegativity, and you can describe it as something like this. Um, an element's ability to attract electrons. You can think of it as how tightly an element holds onto electrons. Okay, so the thing about electronegativity that will help you understand it, if you understood atomic size, this will help, is that smaller elements are more electronegative. Okay, smaller elements are more electronegative. Okay, let's give you a little bit of analogy to help you understand what this word means a little bit better. So, when somebody is a good soccer player or a good basketball player, they're able to have like ball skills. Okay, so if this is my person right here, okay, and let's say this is the soccer ball. Okay, in our analogy, the person is the nucleus and the ball is an electron. So um, the closer the ball is to the person means they have better ball skills, and the ball skills is like the element's ability to attract electrons in our analogy. Okay, somebody who you see dribbling a soccer ball like super far away, shows they don't have too much control. They don't have too much control of the ball. Or if you see somebody dribbling a basketball, or if you see somebody dribbling a basketball like this with their arms way out here like that, it'd be really easy to steal that basketball from that person. So in our analogy, someone who's able to dribble the ball close to them and keep the ball tight and close is like an element having greater electronegativity because um, that element would be smaller compared to like the person who's dribbling the basketball far away or who's kicking the soccer ball really far away. That element would be larger. Okay. So what does this mean for two different elements that are in the same row? For example, we'll use our lithium and chlorine, or excuse me, lithium and nitrogen example again. So lithium, this guy will be lithium, and this guy will be nitrogen. Um, okay, and we'll put nitrogen's electron a little bit closer, right? So we know this is obvious that nitrogen is the smaller the smaller atom, and the smaller atom lets us know that the protons are attracting the electrons with greater strength, making it a smaller atom, causing it to have more electronegativity. So you could say that in our analogy, this person has better ball skills, ball handling skills than this person over here, because the number of protons, maybe you could say, are the number of soccer lessons this person has had, compared to the number of protons, which are the number of soccer lessons in the analogy that this person has had. So why is all of this important? Well, all this is important because at the microscopic level, if we know how electrons are interacting with other electrons, then at a more macroscopic level, we can figure out how compounds will be formed. And then we can discover new compounds, which will surely, like it has in the past, influence our quality of life. For example, like plastic or Tylenol or um, a vaccine to the novel coronavirus. All right, let's do some stuff. Warm up. Draw the Lewis structure for the following elements and their MCIs. That's most common ions. So here's the Lewis structure. Ready for bromine? We're finding bromine on the periodic table. We found bromine all the way right over here, number 35. And we notice that bromine, counting from the left and skipping this middle section, we count like this: one, two, skip the middle section, three, four, five, six, seven. Bromine has 7 valence electrons. Those are the electrons on the outermost shell of the bromine atom. So what we're going to do is draw the Lewis dot structure. So that means we've got to do Br and draw 1, 2, 3, 4, 5, 6, 7. And that is Lewis dot structure for bromine. Oh, make sure those are visible for you. 7 dots only, not 8, not 6, must be 7. Okay, now we want to draw the Lewis dot structure for the MCI of bromine. Well, MCI is the most common ion, and when bromine becomes an ion, it gains 1 electron to have the same amount of electrons as the closest noble gas, krypton. And krypton has how many electrons, how many valence electrons, those electrons in the outermost shell? Well, the rows are the shells, and krypton is in row 1, 2, 3, 4. So bromine ion, remember, has this many electrons. So we're going to count from the left, skipping the middle section like this. 1, 2, skip the middle section. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And so bromide is the most common ion with a -1 charge, has 1, 2, 3, 4, 5, 6, 7, 8 dots in the Lewis structure. And we just did it. That is bromine, the atom, and bromide, the ion. They're Lewis dot structures for both. Okay, let's do potassium as a warm up. Potassium. Okay, okay, ¿qué pasó? So potassium is number 19 right here. And we know that potassium is in the 1, 2, 3, the 4th row as well, just like bromine was. But potassium only has the 1 electron because there's only 1 box in the 4th row for potassium. So potassium's Lewis dot structure just looks like this: 1 dot, boom, done. That's it. Now potassium's most common ion. When potassium becomes an ion, it doesn't gain all these electrons. Like, remember, bromine gained the 1 electron. It's not going to gain all these electrons to have the same number of electrons as krypton. It's going to lose its 19th electron so that it has the same number of electron as the closest noble gas, argon. So argon right here. Well, let's first think about the symbol. The symbol is potassium plus 1. Why? Because it lost that one electron, and now the difference between protons and electrons is just 1. 19 protons, 18 electrons. But it has the same Lewis dot structure as argon, which means it will have 1, 2, 3, 4, 5, 6, 7, 8 dots around the Lewis structure. So that's going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and just as a reminder, potassium ion has 8 dots because it lost a shell. Where here, potassium atom, where there is 1, 2, 3, 4 shells with a 1 valence electron on the outer shell. When potassium atom loses an electron, it loses that 1 electron, it loses that entire shell. So now potassium ion only has 3 shells. 1, 2, 3, with all 8 electrons on the outer shell, just like argon. Okay, and that is a review there. So electronegativity, we talked about that. So let's start answering some of these questions. Electronegativity is how tightly an element holds onto its electrons. It's the element's ability to attract electrons. Which element is more electronegative, fluorine or beryllium? Well, if we look at fluorine right here, it's on the second row, and it's also and beryllium is also on the second row as well. So which one is more electronegative? Well, fluorine has 9 protons in the nucleus, while beryllium has 4 protons in the nucleus. So the fluorine's 9 protons is going to have a greater electromagnetic pull on the electrons in the electron cloud compared to beryllium's 4 protons, which will have a weaker electromagnetic pull of attraction or force of attraction on the electrons in the electron cloud. So which element is more electronegative? We'll say fluorine. Fluorine is more electronegative. Why? Because if we wanted to explain why, like if I asked this other question, why, we can say 9 protons attract electrons with more strength compared to beryllium's 4 protons. Yep. Okay, which one is more electronegative? Sodium or lithium? Let's find sodium and lithium on the periodic table. So sodium is right over here and lithium is right here. Well, this is an easy one because sodium has more shells than lithium, meaning lithium is going to be smaller, meaning those electrons are closer to the 3 protons. So lithium is going to be the more electronegative. Well, you might be saying, well, Mr. Edwards, sodium has more protons. That doesn't make sense. Well, those protons are farther away from those electrons are farther away from those 11 protons because sodium has electrons in a third shell compared to lithium having electrons only in 2 shells. So the distance between the protons and electrons matters, and also the number of protons matters within the row. Okay, within the row. So this answer is lithium. Why? Because lithium has less shells, meaning a smaller distance between protons and electrons. Another way you can think about it is if you ever played with magnets and you have the sides that are attracting, don't you kind of have to get them a little close? You know what I mean? Don't you have to get them a little close before they start attracting? If you pull them far away, then it's not going to work. Okay. I'll let you do C. C is going to be your question. The answer is nitrogen. Okay, so the question here is, what is the trend or pattern for electronegativity on the periodic table? Well, on the periodic table, the smaller the atoms are, the more electronegative. So as you go up, it's more electronegative, and as you go across within each row, it's more electronegative. So you can think about it like this. The trends on the periodic table is if you go up, it's more electronegative, and if you go right within each row, it's more electronegative. So we could say that this is increasing in electronegativity. Okay. Yep. Next example. Organize the following atoms from least to greatest uh, electronegativity. So we got Fe for iron, O for oxygen, Cl for chlorine, and Br for bromine. So Fe is right here. Oxygen is right here. Chlorine is down here, and Br is down here. So it looks like we just have two elements within one row. That's the Fe and the Br. Okay. Um, and they're the ones with the most amount of shells. So they're going to be, one of those is going to be the least electronegative. And that one that's going to be the least electronegativity is going to be iron, because iron has 26 protons, while bromine in the same row has 35 protons, meaning the 35 protons can hold those electrons and electron clouds more tightly. So the least electronegative is going to be iron. So we'll start with iron, and then we'll write bromine as the next one. And then the other ones we have left are chlorine and oxygen. And chlorine's in the has 3 shells, while oxygen only has 2 shells. So that's easy. Oxygen's electrons will be held more tightly because there's only 2 shells, and the distance between the electrons and the protons is smaller compared to the distance between electrons and protons in chlorine. So it should go like this: iron, bromine, chlorine, oxygen. That's from least to greatest electronegativity. Everybody say electronegativity. All right, atomic size, how big an atom is. That's what size means, is how large something is. Which atom is bigger, beryllium or barium? So let's find beryllium right here. Be, let's find barium. There it is down there. Well, this should be easy. Which one's larger? Is that the question? Oh yeah, which atom is bigger? Which atom is bigger is the question. Well, barium has 6 shells. 1, 2, 3, 4, 5, 6 shells, because it's on the 6th row of the periodic table, while beryllium only has 2 shells because it's on the 2nd row of the periodic table. Barium is obviously bigger. Circle barium. Phosphorus or sulfur. Now, this one right here is phosphorus, and this one right here is sulfur. Which atom is bigger, it's asking? Well, remember, sulfur's 16 protons has a greater electromagnetic pull on the electrons in the electron cloud, meaning that the electrons are going to be closer to the nucleus inside of a sulfur atom, which means phosphorus is going to be the bigger atom because it only has 15 compared to 16 protons. Think about them like magnets having control of the electrons in the electron cloud, because positive protons attract the negative electrons. What is the trend in periodic table for atomic size? Well, atomic size will increase as we go down the periodic table because we're increasing in the number of shells, and it will decrease from going left to right. So we can say increase size, and then from left to right within the row, right? Within the row, it's going to be decreasing. All right, everybody, just making a quick change so that we could be somewhat consistent. This might be easier to memorize the trends. So instead of saying going down, we're increasing in atomic size. We're going to point the arrow up and say decreasing in atomic size. And what that does is it allows us to be consistent with our trend in electronegativity. So in electronegativity, it's the exact opposite. When we go up and right on the periodic table, that's increasing electronegativity, while we go up and right on the periodic table, we're decreasing in atomic size. So that's that. Okay, we're going to organize the following elements in order from smallest to largest. So we're going from smallest to largest this time. So let's analyze the elements we got. We got lithium, fluorine, Y for yttrium, and CS for cesium. Where is CS? I don't know where that one is. Where'd it go? I blanked on that one. There it is. Way down here. Way down here. Okay, so let's find them. Lithium, number 3, right here. Fluorine, number 9, right here. Those are in the same rows. Yttrium, right here, number 39. And finally, cesium, right here. Okay, well, between yttrium and cesium, that's easy because cesium has way more shells. So the electrons are further from the nucleus. So this is a larger atom compared to yttrium. But the question really here is with lithium and fluorine. They're in the same row. But remember, fluorine has more protons. And that means that the electrons are being attracted closer to the protons that are in the nucleus. So that makes fluorine the smallest here. So the order will be fluorine, lithium, yttrium, cesium when we order from smallest to largest. So it would be fluorine. That would be the order right there. Okay, this is going to be a little more difficult because now we're talking about the MCIs, most common ions, okay? So when we're talking about lithium, lithium has the 2 shells. Lithium's most common ion, though, only has 1 shell, okay? Chlorine has, let's go down here. Chlorine has 3 shells. 1, 2, 3 shells for chlorine. I'm sorry, those circles are weird. Chlorine's most common ion also has 3 shells. So how can we tell which one is smallest and largest? Well, we can easily start by going like this. Oh, here it is. So lithium is obviously going to be the smallest compared. Lithium ion will be the smallest compared to lithium. So this will be number 1. Why? Everything's going wrong today. I'm going to cry about it. Okay, this is number 1. This is obviously going to be number 2. So which one's going to be number 3? They both have 3 shells. Well, we have to analyze the difference between their protons and electrons. So chlorine atom has 17 protons and 17 electrons because it's electrically neutral. It's an atom. Okay, chloride ion has 17 protons. Remember, that doesn't change because it's still chlorine. And it has 18 electrons. Well, what does this mean? It means that 17 protons. Why am I still using that marker? It means that 17 protons has a stronger hold on 17 electrons compared to 17 protons having a hold on 18 electrons. So that means this one is smaller. So this is number 3. And this is number 4, the largest one. Okay. As a review, the number of protons compared to the number of electrons matters within each row, and the shells, more shells is a larger atom and has less electronegativity. All right. You are going to do number 8, 9, 10, and 11 on your own. Good luck. All right, now you're going to do number 12, 13, and 14 on your own. Good luck, people.